in an elastic collision, a perfectly elastic collision, we will see a conservation of kinetic energy. And so that means all of the energy from one object is transferred 100% to another object. This happens really clearly in sports. A lot of times a transfer of kinetic energy and elastic collisions. I want you to think specifically about like playing pool, right? We talked about this example at the beginning of our energy chapter. But if I have the cue ball, right? I hit the cue ball and it hits, what are they called? Stripes or solids. Yes. Okay. So if I take the cue ball, it hits ball number 6, right? And that ball 6 is at rest, right? When that cue ball hits, what should the cue ball theoretically do? It should come to a stop, right? A perfect collision would be a complete transfer. If all the energy in the cue ball goes to ball number 6, that ball continues moving at the right angle and the right speed, and the cue ball would come to rest. That would be an example of a perfectly elastic collision. Now, does that happen every single time? Or sometimes the cue ball moves just a little bit before it comes to rest, right? We're going to see those types of things. But we're going to envision that all of our collisions are perfectly elastic, right? That's the perk of working in high school physics world, is that everything works like it's supposed to. Right? We can ignore those other things. But that's an elastic collision. Go ahead. And inelastic collision mean they stick together, okay? Which means that we don't have a conservation of kinetic energy. There's not a true energy transfer. Can anyone give me an example of an inelastic collision that we see in like day-to-day things? I could agree with that. A magnet of some sort, right? Any other examples?
Is this one like the mass that's being hit is bigger than the other one, so it doesn't move?
No. It could be. It's when two things collide and stick together, right? And they move forward as one system.
But they have to move forward. They don't just stay.
Sometimes you could hit and stay, right?
Yes, that's right.
I would say examples would be like if I would tackle somebody, we would see it in football, right? You tackle someone, you fall down as one unit. If you get into like a car wreck, right, and you have a kind of a mangled mess of car, right, that could be considered an inelastic collision. Those are all examples of things we could see that hit and then stick together or move forward as one unit. Okay? What? It's P. Okay, I don't know why. I think all the M's are taken, right? So we don't use M. We use P for momentum. And momentum is mass times velocity. It's a vector quantity, which means it has to have what? What do vectors have to have?
Direction and magnitude.
Magnitude and direction. Good. So momentum has to include a direction. Typically, momentum's in the direction of the velocity, right? We can't have a net velocity to the west and momentum to the east, right? That wouldn't make sense. Our momentum is in the direction of our motion. The unit for momentum is kilogram times meters per second. That's just a derived unit, right? Because I'm taking kilograms for mass times meters per second for velocity. Unfortunately, there's no shortcut unit for momentum, right? We don't get to abbreviate it like joules or newtons or things like that. There's no extra unit for that. So our unit for momentum is clumsy and ugly looking, but that's what it is. Kilograms times meters per second. Momentum is simple to calculate, right? Very simple to calculate. It's very straightforward. We just have to remember that our units need to be kilograms. Okay? So let's just think through this example here. A large truck and a small car are moving at the same speed. Which is more difficult to slow down? Small car or large truck? Yeah, large truck, right? It has more mass. Because they're moving at equal velocity, that component is removed, right? But the fact that the mass of the truck is larger than the mass of the car will tell us it has a greater momentum. And really, when Miles was talking about inertia earlier, mass is really a measure of inertia. The object's larger mass has a larger resistance to change. Okay, so the fact that it has a larger mass is going to give us a larger amount of momentum. Okay, yeah. Straightforward problems here. It says a rolling boulder is found to have a momentum of 4,015 kilogram meters per second east. If the velocity is 16.4 meters per second, what's the mass? It's as easy as it seems. Okay, so I want you to go ahead and plug that in and see what we get here. Right? No tricky algebra. Nothing no funny business here, right? It's just momentum equals mass times velocity. So plug it in and see what you get.
It's 40-15 divided by. You actually got it. I got it all.
4,015 is our momentum, right? What's the variable for momentum? P equals mass times velocity. So all I'm going to do is move that over, and I don't know, I get a mass of what? 200 and what?
44.8.
44.8. What's our unit for mass? Kilograms. Okay. Simple, right? Very straightforward. Okay, momentum will be that way all the time. Then we're going to, then we'll turn up the heat a little bit. But this says this 3 kilogram object is dropped from an unknown height. What is the object's momentum after 1.2 seconds?
Well, that's not in our equation sheet. I quit.
We're turning up the heat a little bit here. Okay, so it says we have the mass. What else do we have?
Seconds, time.
We have the mass and we have time. But does time go in our equation anywhere? No. What do we need to have?
Velocity.
We need to have velocity. So what can we use to help us find velocity? You know my favorite word is kinematics, right? We're going to go back to kinematics and solve for our velocity. Remember when I said kinematics aren't going to go away? They're going to be in every chapter? I meant it. Okay? So we need our velocity, right? We've got to have a velocity. So I know my initial velocity is what if it's dropped?
0.
VI equals 0. VF is what we're solving for. It's vertical here, so what do I know about my acceleration? No. Negative 9.8.
Oh, I can't read the negative.
And I've got my time. What kinematics equation can I use here?
The first one.
I think I can use the first. I would agree. I think I can use the first. Okay. So VF equals VI plus A times T. That gives me a final velocity of what? Okay. 11.76 meters per second. Is that right? Negative. Very good. Has to be negative because it's dropped, right? We're moving in the negative direction. And the math shows me that, right? The math shows me that I've got a negative velocity here. Negative 9.8 times 1.2 gives me negative 11.76. Now I can go find my momentum, right?
We have to do the same thing as V.
Yeah, right. Yep, that's what we're solving for. So momentum equals mass times velocity. And so my velocity is therefore negative 35.28 kilogram meters per second. All right, and we said that momentum is also a vector, which means it needs to be with a direction there. Right? So we're going to include that negative.
Yeah, it's simple as that.
So simple, right? So simple. I didn't say it was one step, but simple. Wasn't that the right? Wasn't that kinematics equation easy?
Yeah.
So easy, right? You've got to be able to identify the fact that I'm missing velocity, right? And then you can find these variables. You know how to do that. It's very capable. Okay? All right, let's move and add forces to it. Okay, we're going to bring a little bit more of it together, okay?
We're just going to go back through all of our equations.
Basically, we're to bringing all of our chapters back. Yep. Yes, sir.
Actually, we're gonna do circular motion.
All right. Yeah, I don't know if we'll get circular motion here, but
We're actually going to do like projectile.
all right. This is now a change in momentum, okay? And so in order for an object to have a change in momentum, there's got to be some force applied. Would we agree with that? Right? An object is moving to the east, it has momentum to the east. So if my momentum is going to change, I have to have a force applied. What's Newton's first law of inertia say? Good.
It's acted upon by another force.
Bingo. Object in motion will stay in motion unless acted upon by another force. So a force is required to change momentum of an object, right? It can't change on its own. So Newton's second law normally reads that. Net force equals mass times acceleration. I'm going to walk you through a little step of equation here. We're going to derive this new equation that we want to talk about here. Okay? So you don't have to, you can just watch for a second. I want you to just watch and just think through this, okay? Net force is equal to mass times acceleration. What can we substitute? What's another equation for acceleration? Change of velocity over time, right? And so now, what does this look like?
That looks like
Mass times velocity.
Okay, but what's that equal to? Momentum. And so now we can get a new equation that says the net force of a system is equal to the change in momentum over time.
It has to be the change in momentum.
Yeah, it's going to be the change in momentum. Now, a lot of times, won't our initial momentum be 0? Right? So it's going to make it a little simpler, but you can keep it at that. Okay, so I would write down that new version of you can write down this one too if you want, right? The second one if you want to, but essentially we're going to get to that conclusion, right? Yeah.
Change of momentum is just like P1 minus P2.
That's right. Right. And your mass really doesn't change. So essentially it's still mass times the change in velocity, right? Because the mass is not changing. It's just the velocity that would be changing. Okay? So we've got a couple different ways we can work through that to solve for our momentum now. Now we can take mass times velocity, or we can take a combination of our net force and our time. All right, so I would go ahead and put some variation of that equation on your equation sheet, whether it's this one, or both. I think those need to be on there. Okay? Let's go ahead and try the next one here. What force is required to stop a 488 kilogram wagon moving at a velocity of 52 meters per second north in 2.3 seconds? So we've got some information here, but not everything that we need just yet. So what force is required? That means I'm solving for the force. It tells me my mass. It tells me my velocity there. So walk me through, is that initial velocity? Is that final velocity? What is it? I hear two different answers. What do we think? It's my initial because it's required to stop. So that means my final velocity has to be 0. So initial velocity would be 52 and final velocity would be 0. My time is 2.3 seconds. So is it prudent for me to use this equation, or is it prudent for me to expand that momentum out and just do it in one step?
Expand it out.
Right? It would make sense for me to just go back to this one. Force equals mass times change in velocity over time. That way I'm not having to put it in multiple steps. Does it make a difference if you just want to solve for momentum first, then plug it in there? No, it makes no difference at all. Yeah.
Alright, so what do we have to figure out whether 52 is like just the final? It's
Be-
going to be 52 minus 0.
That's right. Or it would be 0 minus 52, which would mean that would be negative, right? That's the difference.
So this one's going to be...
It's going to be negative, right? So think about this. My mass is 488. The change in velocity is final minus initial. So yes, although numerically it doesn't matter, it makes a difference with our sign. My time is 2.3 seconds. So if my object's moving to the north, what direction does my force have to be to make it stop? It would have to be negative, right? So we've got to make sure that we're checking our answer for being rational there. So negative 52 times 48 divided by 2.3. I got about negative 11,033. What's our units for force? Newtons. You could have also put 11,033 newtons south, right, and spelled it out. Since we know in this case that the negative is going to indicate south for us, right? You can choose to either put in the cardinal direction. Generally, our rule, remember, is that if a cardinal direction is given, we need to report a cardinal direction. So south would probably be maybe a better answer, but it doesn't matter. Okay? Can we work through multi-step problems? Right? Can we do multi-step here? All right. Try this one on your own. Mm-hmm.
So can you just multiply T over and divide by -42? Or do you have to do it step by step?
What are you solving for? Oh, time. Switch T and F places.
When you okay, so that's
Yeah, you'd multiply over T, divide by F. Yeah, but same thing. Did we remember the shortcut here? Right, if I'm solving for T, I can just switch those spots. So do we remember that shortcut? Okay, good. You guys look like you're already done. Tell me, what'd you get?
4.8.
Good. 4.81. And what would my unit be for time? Seconds. 4.81. At collisions here. The last thing we're going to look at is a thing called impulse. An impulse is just a really fancy word for the change in momentum. Right? So impulse is the change momentum. So delta P is change in momentum. And so I don't know why it gets a fancy name. It just does. But impulse is just the change in momentum. Okay? This just means change in time. We would rarely write it like that. The more appropriate equation, your book has it like this, which is why I put it in there, but we would probably go net force times time, right? That would be more of what we see in how it's written out. This is here. Sure. Okay. Sydney, they need you in the office. Okay, so this would be probably more like we would have written it, right? Net force times time. It's just rearranging the equation we got in the last slide, right? Force equals delta P over T. We're just rearranging that same exact equation.
F net's just like the force.
Yeah. Yep.
I think it's just what it is. It knows what F net is.
Is it changing time?
Yeah, but very rarely do we actually get an initial and a final time, right? Usually it just tells us how long did it take. So I don't even like putting the delta in there because I don't think it's necessary. Okay. This change in momentum applies to each of our objects in the collision. So if we start to look at things that collide, that will cause a change in momentum. This change in momentum applies to each object, okay? I want to look at one other way we can solve for the change in momentum or the impulse, okay? Another way we could solve for the change in momentum is to take mass times the change in velocity, okay? And then this last equation here just shows us that if we have two things equal to delta P, we can set them equal to one another, right? If I can solve for the change in momentum by taking force times time, and I can solve for the change in momentum by taking mass times velocity, I can set them equal to each other. So let me rewrite that last equation in the way that we might like it better, right? Net force times time equals mass times change in velocity, right? That might be the more appropriate way that we would see that instead of that, okay? Two ways that we can solve for this, and then we can just set them equal to one another. We did this in our work chapter 2, right? When we took force times displacement, and then our change in energy. This would be like us saying x equals this and x equals this, right? It's almost a substitution that we're doing, right? We're just setting them equal to each other. So I would put this guy on your equation sheet as well. again, we're just going to kind of make a list of what variables we have and see what equation fits that list the best, right? That's essentially what physics is. If you haven't figured that out yet, that's essentially what it is, right? Make your list, find your equation that fits, okay? All right, let's try an impulse problem here. What force is needed to bring a 75 kilogram object traveling 44 meters per second north to a stop in 2.1 seconds? Okay, what force is needed? So I'm going to solve for force. Okay, we need to assume here that we're always working with the net force, right? We're always going to be looking at that. We're not solving for just the force of friction or gravity or whatever. We're looking at the net. My mass is 75. I've got an initial velocity and a final velocity. And I've got a time. So I can do it two ways. I can solve for the change in momentum and then plug it into my force equation, or I could just use that combined equation that I had. F net times time equals mass times change in velocity. Right? That's probably going to be the easiest thing for me to do there, is just use that combined equation. We're solving here for our net force. So F net times 2.1 equals mass 0 minus 44. Should our force here come out positive or negative? Negative. It's going to come out negative because I'm traveling north. So in order to bring it to a stop, I've got to be having a force that goes to the south.
Negative.
No. Yeah. I got a net force equal to negative 1571 newtons. Yeah. Try this one on your own. You're going to have to use kinematics first. Yes, you will.
32.9. Yeah.
Okay.
Well, originally we got 32.9, but
We rounded up.
Okay. So did you get negative 7.67?
Yeah.
You have to add the negative.
no, because you just use the first one, like
Oh, you solve for time first, then you...
mass times.
So it's negative 32?
Oh, never mind.
No, you don't use that.
I'm with you.
You just did 4.3 times 74.
Mm-hmm.
Just like that.
Just like this. Negative
You
33
don't need times yet.
kilogram meters per second.
No, you don't.
Okay,
Everyone's dropped you.
you can do it.
Of course we can.
I don't think this one needs kinematics, so I think you're good.
Oh my goodness. I'm using the F times time equals mass times velocity. Change.
Maybe I shouldn't.
I got 4.2 seconds. You had -5?
Yeah, 0.6.
You got negative mass.
I think I found.
We're already almost done with this chapter.
Here is collisions. In our collisions problem, our whole goal is to prove the conservation of momentum. What's it mean for anything to be conserved? What's that mean? Cannot be created or destroyed. Good. So momentum of a system before the collision is equal to momentum of the system after the collision, right? That's what we're proving here in a collision. And so this whole system on the left is everything before of object number 1 and object number 2, right? That's what we have, 1s and 2s. After the collision is indicated with this little symbol right up here. Math people, what's that symbol mean?
Don't know yet.
What's this little apostrophe mean when it's applied this way? Prime. Prime. Have you heard that term before? A prime. Okay. V1 prime and V2 prime. Prime just means after collision, post collision. So when you see this little indicator here, V1 prime, that's how I'll say that, V1 prime, that means the velocity of the first object post collision. So we have got to be able to identify variables and systems based on what these indicators mean, right? V1 prime means it's the velocity of the first object, and the prime tells it it's post-collision. V1 is just the velocity of the first object pre-collision. So we've got all these variables that they mean different things. Eventually, we will start dealing with velocity of the first object in the x direction and velocity of the first object in the y direction. Velocity of the first object in the x direction post-collision, right? That's what that would mean. V1x prime would mean it's the velocity of the first object in the x direction post-collision, right? So all of this information here tells us something. It's not like I'm just tacking on variables for fun, right? It all tells us information. So we need to make sure we're comfortable with what those variables mean. In these collision problems, we've got to stay super, super organized, right? Because just of the sheer amount of variables that we have, right? We've got to make sure that we stay really organized. So you'll find a system for how you do the problems, and you'll be consistent with that system. Okay? Did this equation go into your equation sheet? Did you put it on your equation sheet? All right, let's try one here. All right, this says, find the recoil velocity of a 5 kilogram rifle that shoots a 0.05 kilogram bullet at a speed of 120 meters per second. What does recoil velocity mean?
Bounce back.
Yeah, the kickback, right? So when you pull the trigger, that's considered the collision here, right? When we pull the trigger, that's considered the collision. What direction will the bullet go? Forward. What direction will the gun go? Backwards. And so since both of our objects are starting at rest, essentially the momentum in our system is zero, which means that post-collision, the sum of the momentum of the bullet and the sum of the momentum of the gun have to equal zero. Okay, and we're going to walk through the math that goes with that. So let's try and write down our variables here, what we have. All right, I know that I have the mass of the rifle and the mass of the bullet. So we'll just call the rifle object 1. So I'm going to list it as M1 equals 5. And M2 is the bullet, which equals 0.05. Okay, I'm going to make kind of a little list here of all of my variables. I like to keep object 1 listed on top, all of its variables, object 2 listed on the bottom. So V1, the velocity of the gun pre-collision, what is it? 0, right? My object 1 and my object 2, both the gun and the bullet, are not moving prior to the collision.
Is that going to happen a lot?
It's possible. Yeah, I wouldn't say a lot, but it's possible. Okay, do I need to rewrite M1 and M2? Is the mass going to change from the beginning to the end? No. So now I just need to figure out what's the velocity of the gun post-collision and the velocity of the bullet post-collision. V1 prime and V2 prime. What am I solving for here? V1 prime or V2 prime? V1 prime, right? The velocity of the gun post-collision. And the velocity of the bullet post-collision is 120 meters per second. Now, if it told me the bullet was going 120 meters per second west, what would I have to put at the beginning? I would have to include a negative. Remember when we did vector addition and we had to make sure that anything west or south got a negative velocity? The same thing is true here for these collisions. So this one doesn't tell me that the bullet's moving backwards or west or south. So we just keep it positive, but we could expect that our velocity of our gun's going to come out negative here. Okay, but negatives are so important here for direction.
You said that that's going to cancel each other out, like the velocity of the bullet and the velocity of
They're not going to, the velocities won't cancel each other out, but the momentums will become the sum of 0, right? Because of the momentum at the beginning was 0. But let's do the math that works it out. So the equation here is M1 times V1 plus M2 times V2 equals M1 times V1 prime plus M2 times V2 prime, right? Do you see where all those numbers came from into our big momentum of elastic collision equation? Okay. What's anything times 0? 0 plus 0 equals 5 v1 prime plus 120 times 0.05 is 6. So here I'm going to have to subtract that 6 to the other side. So that gives me negative 6 equals 5 v1 prime. And so I'll take 6 divided by 5. And I get v1 prime equal to negative 1.2 meters per second. Okay, and did we expect, at least the direction-wise, did we expect the direction of the gun to be negative? Yeah, those are the things that we've got to check when we finish our problem. Does at least the direction make sense? Sometimes it's going to be hard for us to figure out the velocity, right? Is the velocity rational? But the direction is something that we can for sure always check, okay? That's fine. All right, this says 2 pool balls of equal mass collide. The first is moving at a speed of 3.1 meters per second. The second was at rest. If the collision was perfectly elastic and the first ball came to rest, what's the velocity of the second ball? So we've got 2 balls that have equal mass.
Can't we just set it to something?
Yeah, we can set it to something. Just set it to 1 if we want to, or 2. You can set it to whatever you want. So let's just go ahead and plug in each of our mass as 1. What'd you say? Yeah, if you did it to 0, that would be a problem because anything times 0 is 0, right? So at the very least, just set it to 1. The first is moving at a speed of 3.1. It says the second is at rest. If the collision was perfectly elastic and the first ball came to rest, that would mean v1 prime is equal to 0. We're solving for v2 prime. We're going to find out what that is. Okay. So when I set it into my equation, I'll take 1 times 3.1 plus 0 equals 0 plus 1 times v2 prime, right? Because anything times 0 is 0. Does that make sense why I dropped those out? Mm-hmm. It's like me taking 1 times 0, right? And 1 times 0. Yeah, so what happened? What happened with these objects?
All of them kinetic energy.
That's right. Remember we talked about that at the very beginning. In a perfectly elastic collision, objects will switch velocities perfectly. The thing that has to be true is that their masses have to be identical. If they don't have identical masses, we'll see one ball have more influence over the other, right? But if they have equal masses and the collision is considered perfectly elastic, we will see a true just swap of velocities. Yeah. This one, it says a 22 kilogram bat is swung with a velocity of 16.2 meters per second at a 0.94 kilogram ball moving in the opposite direction of the bat at 34. If the ball leaves the bat at a speed of 42, what is the final speed of the bat? So you need to be really careful with directions here. Can you envision what's happening? Baseball gets pitched, ball gets hit, ball flies outward. What happens to the bat most likely? Is it gonna bounce back? No, right? After you hit that ball, the bat will probably continue in that motion. So we're going to see if that makes sense or see if that comes about. So we need to decide which direction is going to be the positive direction here. Is toward the plate going to be positive or toward the outfield going to be the positive direction? Toward the outfield. Okay, so we just choose that, right? We just made an arbitrary choice there. Toward the outfield is going to be the positive direction. So we need to be careful of that when we plug in these velocities, okay? So M1, I'm going to call the bat, is 22. Object number 2 is the ball, so 0.94. The bat's initial velocity, the bat is moving, hold on. Sorry, the bat is moving 16.2. So is the bat moving toward the outfield or away from the outfield? Toward the outfield. So that means it would be positive 16.2.
Wouldn't the initial swing of the bat be 0?
No, because when the bat contacts the ball, it's in motion. Right? The bat's not sitting there
It's not like
resting. Right? Yeah. right? Okay, so the initial velocity, I didn't mean to put an I there. Sorry, that should just be V1, not VI. No, that's my fault. That's just V1. Velocity of the second object is 34, but it's going to be negative 34 because it's moving toward home plate, which we said was the negative direction. Okay. V1 prime is our question mark. What's the final speed of the bat? And then V2 prime, we said, is the ball. And it's moving 42 meters per second. Is that going to be positive or negative? Positive, because it's going toward the outfield, right? And we said that was the positive direction. Ball leaves the bat, right?
So all we got is the two.
Right? Do you see how in these problems it's so important to make sure you're picking up on all the context clues and reading them very carefully, especially with direction?
But our final speed of that, is that going to be?
I assume it's still going to be positive, right? Because when you hit the ball, your bat doesn't jerk back, right? You continue the swing of the bat through there. So I assume it's going to be positive here. So we're going to go 22 times 16.2 plus 0.94 times negative 34 equals M1 times V1 prime plus M2 times V2 prime. Okay, now we just run them out. Now it's just very simple algebra. In an inelastic collision, we said the masses are going to combine and they're going to move forward as a single unit. So the equation looks the same, except the only difference is that we have the addition of M1 and M2, because we said they're going to move forward as a single unit. And that means there would only be one final velocity, right? Because they're going to move forward together. And so we just have velocity final, right? Not V1 prime and V2 prime. We just have V prime. Okay, so we're going to take this exact scenario, the train, right? Red train, blue train. And we're going to see what happens with this object before and after the collision. Okay, it says if the red train car has a mass of 30,000 and a blue train car has a mass of 20,000, what's the velocity? Let me just go back real quickly. If these objects had equal mass, can you envision what would the final velocity be? No, it would split it in half. 12, right? Because 1, 0, 1's 24, we just take that and split it in half. If they had equal mass, but they don't. Okay, so this says red has a mass of 30,000. And its initial velocity is 24. It says the blue car has a mass of 20,000. And an initial velocity of 0. And so we want to know what is the velocity of the final system. Right, you guys see what I did there? Red and blue make purple. Cute. I know. Sometimes I'm too much. I know. Okay. We would take M1 times V1 plus M2 times V2, which what would it be? 0, right? And that equals M1 plus M2, which would be 50,000 times V prime.
Wow.
I added them together. Yep. So V prime is equal to 14.4 meters per second. Now I want you to just think through this. Which of my cars was heavier? The one that was in motion or the one that was at rest?
In motion.
In motion. So does it make sense that now our final velocity is over halfway? It's over 12, right? That red car had more influence on the blue car than vice versa. Had the heavier car been at rest, our final velocity would have been slower than the average. Does that make sense? Yeah.
Does it matter about the car moving east?
Our final velocity would end up being east, so we could tack east onto the end of that. Yeah.
How heavy would the blue train car have to be before like the red car would stop immediately? You know what I mean?
Oh, okay. You could solve that to figure out. You could just plug in a 0 for this and figure out what would this mass need to be, right? You could work it backwards if you wanted to, but it would have to be, I would think, twice as heavy at least. You'll see scenarios where an object is really large and the first object comes and just bounces off of it, right, and goes backward, right? That could happen too.
That